ready for the opening session. Let's welcome Professor Yong Baek, who will show us about quantum physics.
Thank you very much for the introduction. Is the microphone working or okay? All right. So thank you for the invitation. What I'm going to talk about is quantum spin liquid. So it's going to be a rather short introduction. It's just for an hour. This is a very complex topic. So I'll try to give you some ideas as to what the quantum spin liquid is about. So here is my outline. So I'll give you first some general introduction to quantum spin liquid. And then I'll present the famous solution of Kitaya model. I think a lot of people in the audience probably already know about that. Then there are more than one way to obtain a quantum spin liquid. So in particular, in connection to experiment. So I'll talk about this. And then among many possible ways to get quantum spin liquid, I'll talk about two kinds of system. First one is the so-called Kitaya material. The next one is a quantum spin ice. So in fact, I may actually end up spending more time on a quantum spin ice here. Okay, so I think in the morning, Veronica told you all about the grouping symmetries and symmetry analysis. And this is the traditional way to classify phases in a condensed matter system. So you basically measure all the parameters experimentally to determine the broken symmetry. So for example, by doing an X-ray, you probe the crystal structure, and there you are looking at a charge density modulation. If you use a neutron, then you can look at magnetic structure, then you are looking at spin density modulation. So these are like some direct measurement of all the parameters, and that's essentially what the Ashcroft-Momin textbook is about. So this is what we call a Landau paradigm. And then we have gone to a regime where Landau paradigm does not really apply. So famous examples are like fractional quantum Hall state, these states fractional Chern insulator state, and quantum spin liquid is another example. And these are the examples of, say, topological phases of matter. So open, you may have some kind of topological invariant. Also, this idea that these phases cannot be connected to trivial phases by making some local unitary transformation. And these systems also support what we call fractionalized excitations. Here is some initial ideas about the quantum spin liquid. So by definition, quantum spin liquid does not break any spin rotation symmetry. So we are talking about a quantum paramagnet. Maybe there's no cursor here, okay. So quantum paramagnet, so expectation value of spin is 0. Also the staggered magnetization is also 0. So this is, we are talking about a correlated insulator with no broken translation symmetry. That's why this system is called the spin liquid. And the early ideas about quantum spin liquid is this resonating valence bond state. And this is supposed to be some superposition of valence bond covering. So the idea is that since we are talking about a quantum paramagnet, so why don't we think about, why don't we start with some kind of valence bond state here, valence bond. And this is already a spin singlet. So I start with a spin 0 state to begin with. Then I imagine that I place this valence bond on the lattice like this. And so here, I have some arrangement of the valence bond. And then by construction, such a state has a spin 0. Okay. But unfortunately, if I choose one of these valence bond states, it breaks translation symmetry. So in order to restore the translation symmetry, what you can do, you consider, say, other possible configuration of the valence bond configuration. So imagine that there are many, many possible configurations like that, and you think about a linear superposition of this. And by doing so, if you allow quantum fluctuation between different valence bond covering, then you can restore the transition invariance. And by construction, it's a quantum paramagnet. So this looks like a good way to get a quantum spin liquid. So this is called graduating valence bond state. It's a linear superposition of valence bond configuration. It was initially proposed by Pierre Anderson, for example. So there's the initial idea. So more sophisticated way to define quantum spin liquid is this. So this is supposed to be what you may call a long-range quantum integral topological phases. It sounds very abstract. The upshot here is that this kind of ground state cannot be written as a product state of short-range entangled blocks. And so this idea can be explained like this. So imagine that I'm writing my graduating valence bond state as the superposition of valence bond covering like that. Then let's choose, say, this state as the reference state. Then for this valence bond configuration, imagine that I superpose this pattern on top of this pattern. Then you get some graphs like this. So you just superimpose this image to that reference image. Then you end up with this some kind of loop configuration. So you can think about this sum of valence bond covering as a configuration of some kind of loops. So that you can think about this as a resonating valence bond state. And if you do that, then you can imagine that such a state cannot be connected to the state like this. Say, in this case, for two nearby sites, it's definitely a entangled state, but it's a product of locally entangled state essentially. And so the upshot here is that the string configuration, loop configuration like this cannot be continuously connected to the product state of short-range entangled block, and there's no local limited transformation between these two kind of state, and that's the reason why it's called long-range quantum entangled state. Does it make sense? Okay. So again, if you have any questions, please let me know. Do you guys actually have a pointer, or should I use the cursor all the time? Or the usual pointer doesn't work, right? So the light reflects. Okay, so now another useful thing to think about is a wave function of a quantum spin liquid. So remember that all the important problems in condensed matter is solved by writing down the wave function, like a BCS wave function, say quantum Hall wave function. So why don't we think about a wave function of quantum spin liquid? So to do that, let's start with the BCS superconductor. And for this superconducting state, I'm going to assume that the average number of electrons per site is actually 1. So the lattice is half filled. And let me call G as a Cooper pair wave function of 2 electrons. Then the BCS wave function for such a superconductor can be written as a coherent state of, say, Cooper pair. So that's why there's an exponential function there. And the number of particles in this system is conserved modulo 2. Okay, so let's imagine that I start with this superconducting state. Then the resonating valence bond state can be obtained like this. So then I increase then I add the Hubbard interaction like that. Then imagine that I set Hubbard interaction to go to like infinity. What that means is that I cannot occupy each site by I can occupy the one site by more than 2 electrons. So I should have exactly 1 particle per site. So this way I can freeze the charge fluctuation. So that's the way that I can get the correlated insulator. So now the number of particles per site is exactly 1. Okay, and in that case, one can show that such a state can be written as a sum of a valence bond covering. and the amplitude for each valence band covering can be written in terms of like product of the Cooper wave function. So that's one way to construct superconducting, sorry, the quantum spin-electric wave function. Another game you can play is that now imagine that I put a superconductor on a cylinder. So say I have a two-dimensional superconductor and I place them on a cylinder. Then I thread HC divided by 2e vortex in the center of the cylinder. Then because of this vortex, the wave function, Cooper wave function along the circumference of the cylinder gets to be anti-periodic, but it is periodic along the x, the direction of the cylinder, but along the circumference it has to be anti-periodic. So the corresponding superconducting wave function can be written like this with this G plus minus wave function. Okay. So then, so with this, now imagine that I again freeze out charge fluctuations. So now I have two possible configurations here. I put a two-dimensional superconductor. Yeah. Because of the HC divided 2e vortex, the electron wave function is actually anti-periodic because of this vortex in the center. Yeah, then you get a minus sign. Yes. So that's the difference between, say, this ordinary superconductor here. This guy is periodic in both x and y, but this Cooper wave function is periodic in x, but anti-periodic in y. So that's the difference. No, this is because there's a vortex in the center of the cylinder. The Hubbard interaction gives you insulator. So I imagine that I start from two-dimensional superconductor wrapped around the cylinder here, ordinary superconductor, and there's another one with vortex threading in the center of the cylinder. So as I said, Cooper wave function here is periodic in both directions. Cooper wave function here is periodic and anti-periodic in different direction. But then I increase Hubbard U. So I freeze charge fluctuations, then I get an insulator. The claim is that by doing so, I can get a spin liquid wave function here. I'll get another spin liquid wave function here. And so you can show that in the thermodynamic limit, when the length of the cylinder becomes infinity, then energy of these two states become degenerate. But if you compute the wave function overlap, that goes to 0 in the thermodynamic limit. So what that means is that I generated two ground states. They have exact the same energy in the thermodynamic limit, but they are orthogonal to each other. So they have to be two different states. So this tells you that by doing so, for this infinite cylinder, I generated two degenerate ground states. Two degenerate ground states. I have two degenerate quantum spin liquid states. So notice that if I consider two quantum spin liquid states like this, then locally, if you do any measurement, you cannot distinguish these two states at all. So any local measurement wouldn't tell you which one is actually what you're measuring. So there's no local way of distinguishing them. You need the global information about these two states. Only then you can tell that they are different states. So you can use the same argument, say if you wrap your two-dimensional quantum spin liquid on the torus, and then you can show that there are four degenerate ground states using basically the same argument. Okay. So is that clear? Any question? Right. Great. So again, if I do that, then the resulting state may be written in terms of superposition of valence band covering. And here amplitude is given by this Cooper wave function. But in this case, notice that in one case, you should use periodic wave function, but in the other case, anti-periodic and periodic wave function. Good. Another thing you can appreciate is to imagine that now I go to a very, very short coherence length limit. So the valence bond you are thinking about is just between the nearest neighbor site. It's a very short Cooper pair when you are considering superconductor from the beginning. Then when you consider even another combination like this, then what you can do is you take a one column on the lattice, and you notice that for the even combination, the line will intersect even number of valence bond. In the other case, it will be intersecting odd number of valence bond. So in fact, if valence bond configuration fluctuate, for example, in this case, 2 became 0. In the other case, there's a fluctuation between 3 and 1. So you will always intersect even number of configuration, like even number of valence bond like this. Here you will always intersect odd number of valence bond. So topologically, you cannot go from one configuration to the other at all. You always have to stay in one sector, and that's the way that you generate a non-trivial ground state degeneracy. Okay. So, any question? Great. Okay. So what about elementary excitations of quasiparticles? So again, you can use this argument here. Remember that in superconductor, elementary excitations are for quasiparticles. And remember that I said I'm starting with a configuration where the average number of electrons per site is exactly 1. So there's a particle symmetry. Because of that, if you make a quasiparticle, it's always a superposition of particle and whole. For the half filling, it's this equal weight of particle and whole, right? So you can think about such a quasiparticle having a 0 average charge because of particle symmetry, but they also carry a spin half quantum number. Now I jack up again how about you, so that I freeze out all the charge fluctuation. Then the 0 average charge becomes exactly 0. There's no charge fluctuation anymore. But it still carries a spin half quantum number. So resulting particle does not carry any charge, but it still carries a spin half quantum number. And that's the way that you could obtain say what you may call a spinon excitation. So this is an example of fractionalized quasiparticles. Okay, so you can think about this as a fractionalization of electron in the sense that the spinons only carry spin quantum number of electron, but it does not carry charge quantum number at all. Okay, so that's one way to think about elementary excitations on top of the ground state. So this is an example of some non-trivial fractionalized excitations. Okay, so all of these ideas sound very abstract, but actually there is a exact solvable model of quantum spin liquid. So this is famous Kitae model. So here the model is very simple. For different bond direction, we have a different kinds of Ising interaction. So for example, for the blue bond, we have an Ising interaction among X component of spin. For the red bond, we have Ising interaction between Z component of spin, etc. So in this kind of model, if you try to solve this model classically, if you try to solve this classical model, then you realize that there is no one spin configuration that will satisfy all the interactions here. So as a result of that, you end up with exponentially large number of equally unhappy spin configuration. So they all have the same energy, okay? And there are exponentially large number of them, but none of them is happy in the sense that they cannot really satisfy all the Ising interactions that depends on the bond direction. So you end up with this large number of state. So then you can imagine that why don't I think about some linear superposition of this classically degenerate state, and perhaps this is a good candidate for quantum spin liquid. And this problem can be solved using this representation. So you write your spin operator in terms of bilinear of, say, Majorana fermions. So remember that Majorana fermions are the real fermion, the complex conjugate of that fermion is basically the fermion operator itself. So for each alpha component, you take one of these B component of minor fermion, then multiply that to C minor fermion. If you do that, then if you plug in this representation to the spin, then you end up with some kind of 4 fermion interaction. But what happens is that this combination of B minor fermion, this combination actually commute with the Hamiltonian. So what that means is that I can think about this combination as just a number. And when Uij alpha becomes a number, then this becomes a quadratic Hamiltonian. And we are all trained to solve quadratic Hamiltonian. So we can solve this model. So if you do that, then not surprisingly, you get some kind of Dirac fermion like spectrum. But before we go there, one interesting or important element of this exact solution is that if you think about a product of 6-spin operator like this around the hexagon, and this operator, loop operator, commute with the Hamiltonian. So this loop operator itself becomes a constant, and it can have an eigenvalue plus minus 1. And it turns out that in the ground state, you can set all the Uij to be plus 1, so that the loop operator eigenvalue is also plus 1. In this case, we say the ground state is in the zero flux sector. There is no finite flux around the hexagon, and that's the reason why WP, the loop operator, is Plaquet operator or loop operator becomes plus 1. In this case, again, since Uij is a number, you solve a quadratic Hamiltonian like this, and then just like the solution for the graphene, you get a minor fermion with the Dirac dispersion at the K point in the Brillouin zone. So that's basically the solution. So you end up with C minor fermion excitation with the Dirac dispersion. But I told you, yeah.
So if I go back to that slide,
Yes.
how would it shoot for the U opposite of the slide?
Mhm.
It looks like the W is still. So do I just get a kind of gauge transform? Like
Yes.
ground?
Yeah, it's basically the same ground state, just a gauge transformation. Yes, exactly. But on the other hand, you could choose a non-uniform Uij configuration. They still commute with Hamiltonian. This is still an eigenstate, but there's a higher energy state. It's not the ground state. Yeah, yeah, you're absolutely right. Okay, now, yeah, go ahead. So minor fermion creation and destruction is basically the same, because the minor fermion operator dagger is minor fermion itself. Yeah, but what you get is, like, for example, if you have SECT interaction, then you would get say BIXC, BJXC. So in that way, you get a 4 fermion interaction, right? So, but then it's just that this combination becomes a number. So that's why the model can be solved. Okay, it's pretty simple once you know the solution. Okay, great. Okay, so so I told you that you can get Fallon's molecule starting from a superconductor. So what about this example? So it turns out there's a very interesting connection to superconductor here. So remember that these B and C minor fermion operators. So imagine that we take this combination of C and BZ minor fermion and this BX and BY minor fermion combination. And since minor fermion is basically half of the usual fermion, by making this combination, I can make a ordinary fermion or complex fermion in this way. So then I can define, say some kind of upspin fermion and downspin fermion operator like this. If you use this representation, you can show that if I go back to the spin operator, the spin operator can be written in terms of these F fermions in some bilinear form like that. Okay, but with the constraint that the F fermion number per site is exactly 1. Okay, so this I just do a basis transformation, then I end up with this new representation where spin operator now can be written in terms of this ordinary fermion. But with the constraint, the number of fermion per site is exactly 1. Okay. If you do this, then the model that we wrote down using Majorana fermion can be rewritten like this. So here I have some kind of a fermion hopping term between nearest neighbor site. Here is some kind of a pairing term. It turns out this pairing is some kind of a spin triple pairing, not a spin single pairing. But importantly, it looks like a vicious Hamiltonian, but with the constraint that there's exactly 1 particle per site. So by definition, it has to be an insulator. So in fact, by looking at this, what the insight you get is that if you start from a spin triple superconductor where the average number of particles per site is 1, when I jack up the U interaction to infinity so that I freeze out all the charge fluctuation, and that's the way that we get basically K-type spin liquid. So you can think about that K-type solution as the basically failed superconductor. So there is a natural connection to superconducting state. Okay, is that clear? Yeah, cool.
So are these just labels for the top 2 definitions of the fermions, or if I do, for example, a time reversal on that fermion, I will get the second one, as in it switches the flavor of my alarm between time reversal?
Yeah, so Fi of dagger will be Ci minus I Biz, for example, because C and B is not going to change anything, right?
Not dagger, I mean apply a time reversal operator.
Yeah, then there should be a up spin to down spin. Yeah. So there's a time reversal operator. Yes.
And that would change the flavor of the myelana, like take a C to a B or something.
Yeah, you can think of this way, but again here, up and down. Yeah, so you have to define a time reversal operator accordingly to be compatible with the definition of this minor fermion. So you have to so you can define a time reversal operator for the fermion, ordinary fermion. Then you can define a time reversal operation for the minor fermion accordingly. But there is a consistent description. Okay. Any other question? Yeah, go ahead. Yeah, so there are a bunch of papers studying that. So if you start from a K-type spin liquid, if you dope it, in fact, you can get a spin triple superconductor. So what actually happens is that you essentially promote a charge fluctuation so that you can go, basically you're going back. So spin triple superconductor. Yeah. Okay, great. So there's no other question. Okay. So now notice that if imagine that in this model, for some reason, your pairing is basically 0. Then if this pairing is 0, then the resulting Hamiltonian only has a hopping term. So then the model is invariant under this U1 gauge transformation. If generally, if delta is non-zero, then the gauge transformation is only Z2. So you just change the sign of the F fermion, then there are corresponding changes to hopping amplitude and the pairing. And under just this discrete Ising transformation, the Hamiltonian is invariant. So that's the way that the system becomes some kind of gauge theory. So if delta is 0, then the theory becomes a U1 gauge theory. If delta is finite, then the theory becomes what you call Z2 or the Ising gauge theory. So sometimes, so the situation like this is called that ground state is a U1 spin liquid. In a situation like that, then we call ground state as a Z2 or Ising gauge theory. So that's the terminology that you will encounter in the literature. Okay. Any question here? Okay. So another thing I like to mention is that for the Kitai model, essentially the hopping in amplitude T and delta is basically frozen. So the Kitai model, either U1 gauge field or the G2 gauge field, for example, like A. These are not dynamical degree of freedom. It's basically frozen because these become some kind of complex number. But for more generic system that's not exactly solvable, one can show that these objects are actually not frozen. These are also dynamical degrees of freedom. So in those cases, both U1 and G2 gauge field can fluctuate. And the reason why the guitar model can be exactly solved is because you are basically freezing the fluctuation of this gauge degree of freedom. So that's the reason why the solution is very simple. Okay. Yeah. Yeah, so that picture just gave you one of the possible valence bond configuration. As I said, spin liquid is a linear superposition of all of those. And that's the way that you recover the uniform, say, density solution. Yeah. So each one of them breaks translation symmetry, but if you consider linear superposition of all of them, then you restore the translation symmetry. Okay. So imagine that those spinons are fermions. Then there are some very distinct thermodynamic signatures of such a quantum spin liquid. So first question you may ask is whether spinon pairing actually exists. The spinon pairing doesn't exist. Then the ground state is a U1 quantum spin liquid where there is an emergent U1 gauge field. There's a emergent U1 gauge transformation associated with it. If your spinons are gapped, then the only low energy excitation you have is basically a gauge field. So in this case, for example, if you're in 3-dimension, your heat capacity should be proportional to TQ, right? Because all the U1 gauge field of photons have a linearly dispersing mode. So that linear dispersion relation will give you T cube heat capacity just like a phonon in 3-dimension. It turns out such a state, this kind of state is actually unstable in 2-dimension because of the what people call Polyakov's instantaneous effect. So situation like that is only possible in 3-dimension. If your spinons are gapless, for example, if your spinons have Dirac dispersion, then your heat capacity may be proportional to T square. If your spinon has a Dirac dispersion, if your spinon has a Fermi surface, then just like the ordinary electron, with the Fermi surface, heat capacity should be proportional to T, very naively. But it turns out by including fluctuation, this power law is actually changed. So for example, in 2D, heat capacity should be proportional to T to the 2/3. In 3-dimension, there's a logarithmic correction. And this is including basically fluctuation effect of the gauge field. When there's a pairing, there is a Eigengauge theory or G2 spin liquid. Your U1 gauge field is gapped because of the Meissner effect. Your photon acquires a mass. Again, if spinons are gapped, then all the excitations are gapped. So you have to end up with the exponentially activated heat capacity. But if spinons are gapless, again, say, imagine that you started from D-wave superconductor, but by including, basically by freezing charge fluctuation, you get a spin liquid. In this case, again, in 2-dimension, if you start from a superconductor like that, then heat capacity should be proportional to T squared. So there are some definite consequences for thermodynamic signatures for depending on what kind of spin liquid you basically have. Okay. Is there any question about this? But this is assuming that the spinons are fermions. Okay. Good. So there was this exact solution of guitar, but that's not the only way to get a quantum spin liquid. So there are at least three different ways that we could get a quantum spin liquid state. Actually, wait, if I get my, just a moment. So there are at least three different ways to get a quantum spin liquid. The first route is to use the lattice geometry. So this is what people call a geometric frustration. So famous examples are like you consider, say, corner sharing triangles in 2 dimensions. That's the Kagome lattice. There's a 3-dimensional version of that. This is called the hyperkagome lattice. So here you have a corner sharing triangles in 3 dimensions. So that's why it's called hyperkagome lattice. And another important lattice structure is a pyrochlore lattice structure in 3 dimensions. And this one is a corner sharing tetrahedron. So in all of these cases, even if you put Heisenberg model, the spin potential invariant Heisenberg model on these lattices, and if you solve a classical model, then you end up with, again, exponentially large number of equally unhappy spin configuration. There is no single classical spin configuration that can minimize the energy. Okay. So because of this, again, by thinking about some linear superposition of such a classically degenerate state, one can imagine that in those lattices, some kind of quantum spin liquid may actually arise. So these are the representative material candidate. For example, there's this famous material called the Hubbard-Smithite. Here, copper gives you spin half spin on the Kagome lattice. For the hyperkagome lattice, the iridium will give you some kind of effective spin half degree of freedom on the sides of the hyperkagome lattice. And this is more recent example of cerium-based pyrochlore system. The cerium gives you some kind of effective spin half degree of freedom on the sides of the pyrochlore lattice, basically at the sides of the say each tetrahedron. Okay, so this is one way to get a quantum spin liquid. Second way of getting is using the nature of the interaction. So the most obvious example is the Kitae model that I told you about. So remember that for the Kitae model, the interaction depends on the bond direction. So depending on the blue, red, and green, we have a different Ising interaction. Because of that, again, if you try to solve a classical model, you end up with exponentially large number of classically degenerate spin configuration. So in this case, the honeycomb lattice itself is not a frustrating lattice. If you put a Heisenberg model, say, on the honeycomb lattice, you just get a very boring AB sub lattice antiferromagnet as the ground state. So it's definitely the lattice structure doesn't really give you frustration, but interaction does. Okay, so that's the way that you can probably get a quantum spin liquid state. Another more recent interesting example is this ytterbium system. In this case, it's not a point-dependent interaction, but you basically use the further neighbor interaction. So here it's a nearest neighbor interaction. If you have a sufficiently large, say, next nearest neighbor interaction, then you can show that you get into a frustrating situation again. So this is the, say, proposed phase diagram depending on the elements in this compound. But this, for example, on the triangle lattice, if you only have a nearest neighbor interaction, then it's known that the ground state is what we call a 120-degree magnetic order. But the proposal is that if you have a sufficiently large further neighbor interaction, then you suppress the magnetic order, then you may get into a quantum spin liquid. So in that sense, either you can use point-dependent interaction or the further neighbor interaction, and that's the way that you could achieve a quantum spin liquid state. Third way of doing it is to actually use a charge fluctuation. So imagine that I start from a Hubbard model, and if I go to a very large U limit, you know that that's the way that I get a Heisenberg model, nearest neighbor Heisenberg model. So this describes such a situation. Basically, your exchange interaction between nearby site is given by say exchange coupling is order of Hoping square divided by Hubbard U. So you can get that. But if U is not too large, if U is finite, then you can go to the next order. In this case, the exchange interaction is order of, say, Hoping to the first power divided by your Hubbard U to the Q power. You can imagine keep going like this. The second order gives you what people call a ring exchange model. So it's a four spin interaction like that. Okay. So again, if you only have nearest neighbor interaction on the triangle lattice, for example, then you get a 120-degree order. And you can show that if you put a ring exchange model, ring exchange term, and when the ring exchange term becomes sufficiently large, then again you can destroy the antiferromagnetic order, you get into a spin liquid. And of course, if U becomes very, very small, then you just get a metallic state. So there should be a series of transitions from 120-degree magnetic ordering on the triangle lattice, then you go into a spin liquid promoted by this ring exchange interaction. Then eventually you will have to go to metallic state. And this kind of mechanism is valid only when you're very close to metal insulator transition, so that your U is actually not too large, but it allows some charge fluctuation. So situation like this actually exists for organic material like that. So these are the famous examples of organic material where U by T is basically tuned by applying a pressure. So in ambient pressure, it's an antiferromagnetic insulator, but you apply a hydrostatic pressure, then you decrease the strength of the U, and that's the way that you promote a ring exchange interaction. Then you can get into a spin liquid state. Yeah. This mechanism in principle work for any lattice geometry. It's just that for this material, the spin half degree of freedom forms a triangular lattice. Okay, so 벌써 good? Great. Okay, so so a little more details about how you may actually get a K-type interaction in the real material. So this is the famous mechanism to generate a K-type interaction. So either you consider iridium 4+ ions in this kind of material, or ruthenium 3+ ion on the ruthenium trichloride material. So you have 5d5 or 4d5 spin electronic configuration. So for example, if you start from say 5d electron, then under crystal electric field environment, this 5d electron orbital split into T2z and EZ orbital. But now if you consider just the T2z orbital, then they actually act like an effective angular momentum one state. So remember that T2z electrons are like dxy, dyz, dzx orbital. And they actually act like an effective angular momentum one state. Now, if you include the spin-orbit coupling, then you have to add angular momentum 1 and the spin half quantum number. So you generate effective J, either is half or 3/2. It turns out that the level is such that, sign is such that the J effective 3/2 degree of freedom is lower energy. J effective half degree of freedom is higher energy. Since there are 5 electrons, 4 of them goes here. Remaining one comes here. So that's the reason, that's the way that I can generate some kind of pseudo spin half degree of freedom. And using this, I can build a spin model. And it turns out that that's the way that we could generate a K-type interaction. And the reason why you can generate a bond-dependent interaction is because if you actually look at the wave function of this J effective half spin, and it's a linear combination of different orbital content, like xg, yg, xy orbital content, and xg, yg, xy orbital content. So because of this orbital dependence, this pseudo spin knows about the bond direction. So when you actually construct the spin model, that's the way that you can generate this bond-dependent interaction. So in fact, this bond-dependent interaction is obtained by considering what we call a superexchange interaction. So for ruthenium chloride, these are the d orbital. This is the chloride orbital. So you go through the exchange process, means that you're just transferring electrons. Then that's the way that you generate a spin interaction. So the superexchange interaction gives you a cation interaction. In real material, there's also a direct overlap between d orbital. And unfortunately, this direct overlap is actually quite large, especially for 4D or 5D orbital. Therefore, this direct exchange also gives you another interaction. So you can generate a cation interaction from superexchange. That's nice. But direct exchange also exists, and unfortunately, that's not small. So that generates another interaction, like a Heisenberg or what people call a gamma interaction like that. It's also a bond-dependent interaction. So because of the fact that there are significant other interaction, for this material, for example, the ground state is actually not a spin liquid. It's you end up with this zigzag magnetic order. So if somebody asks me like how to realize the pure cation model, then I would say you want to promote a superexchange interaction, but you want to suppress the direct exchange. So one way to get that is to make the lattice constants very, very large. Imagine that I have a God-given ability to make the distance between ions very, very large. Then my direct overlap will be highly suppressed, but my superexchange may still be significant. So that way, you could promote a very large cation interaction. Unfortunately, at the moment, for most of the materials that we know, the J and gamma and other interactions are sufficiently large so that most of them actually go into a magnetic order state. So one reason why the cation material got a lot of attention was because of this possibility that you could generate what people call non-abelian spin liquid. So Kitaev already showed this in 2006. If you add a G-man interaction to the cation model, and assuming that my applied field is very small, and if I do a perturbation theory, then I can generate this 3-spin interaction term like that. The coefficient goes like magnetic field to the cube. And this magnetic field immediately gap out the Dirac-Majorana fermion. So you have a finite energy Majorana fermion. There's a mass gap. So the bulk is gap. Because of magnetic field, you break tiny Boston symmetry. But at the boundary of the system, there are propagating Majorana fermion. And there's a chirality associated with it because time Boston symmetry is broken. And then you can look at thermal Hall conductivity carried by this Majorana fermion at the boundary. And you can show that it's proportional to some number. And this number Q represents the number of degrees of freedom. So if boundary mode was carried by the ordinary fermion, then the number was supposed to be 1. But since Majorana fermions are like half of the ordinary fermion, the number turns out to be half. So it's supposed to be half quantized, if you like. So depending on the orientation of magnetic field, along some direction, it's half quantized. Then, if you change the direction of the magnetic field, you can switch the sign of the thermal Hall conductivity. Along some direction, it should be 0. So that will be the prediction from such a theory. So following this idea, there was this famous experiment by Yuji Matsuda in Japan. So he applied a magnetic field, say along the in-plane direction. Okay. Now remember that if you apply a magnetic field along the in-plane direction, there is no Lorentz force anyway, right? So this is what people call a planar thermal Hall effect. So you create a temperature gradient. Here's the high temperature, low temperature. Then you measure the thermal gradient along the transverse direction. And that way you can measure the thermal Hall conductivity. The claim here was that by applying a magnetic field, you can destroy the zigzag magnetic order. So, and then you may get into some very boring paramagnet, polarized paramagnet in high field. But the claim was that it looks like there may be an intermediate state before you get there. And in that regime, looks like the thermal Hall conductivity seems to be half quantized. Okay, so this generated a lot of enthusiasm. But remember that the actual the model that describes the system is actually not a pure guitar model. So strictly speaking, this scenario does not really apply to the real system. So if this is true, then something else may be going on here. So the idea was that imagine that there is some control parameter, G. It can be a pressure or magnetic field or something. So the ground state, we know the ground state is a zigzag magnetic order. And by controlling this interaction, I may actually realize the spin liquid state. But the real system is here, not here. But then you apply some magnetic field or some other control parameter. Then perhaps the phase boundary moves. Then this spin liquid becomes a chiral spin liquid that I talked about. And the zigzag magnetic order is suppressed. Phase boundary moves. Eventually, you get a polarized paramagnet, but hopefully, you may be able to achieve chiral spin liquid state like that. And that's the idea. And based on this idea, they propose a phase diagram like this. Okay, so this generated a lot of enthusiasm. Perhaps we could realize this chiral spin liquid. But I have to say, at this point, it's very controversial. Some experimentalists actually don't quite get this half quantized the thermal Hall conductivity. So a lot of debate going on. And theoretically, all the theoretical models that people proposed, it turns out, but at least for those models, there is no intermediate state. So this kind of discussion should be investigated further. Okay. So in the next 7 minutes, I'd like to describe the physics of quantum spinons. I don't think that I have time to describe the real material, but I can explain the idea here. So let's think about pyrochlore lattice, the corner sharing tetrahedron. So imagine that I have an Ising model, a nearest neighbor Ising model. It's a classical system. Then you can show that the Ising model can be written as like this. You first consider sum over all the G component of spin in each tetrahedron. Then you scale them. The sum over all tetrahedron. If I do that, then every side is counted twice. So I have to correct the mistake. That's the reason why I have to multiply one half factor there. Then up to constant, one can show that these two Hamiltonians are the same. So classically, in order to minimize the energy, it's clear what to do. I have to make this cluster spin to be 0. The spin sum on each tetrahedron has to be 0. And by doing so, you realize that the spin configuration that satisfies this constraint is like this kind of 2 into our configuration. So two of the spin goes into the center of the tetrahedron. The other 2 goes out. And for each tetrahedron, I have 6 possible configurations. If I tile the entire lattice with this configuration, I end up with, again, exponentially large number of spin configurations. So again, at the classical level, I have an exponential degeneracy of the spin configuration. So now if you add transverse interaction, then you immediately generate quantum dynamics because G component and the transverse spin interaction, they don't commute. So now assuming that my Ising interaction is much, much larger than the transverse interaction, I can do a third of the degenerate perturbation theory. Then I end up with this famous ring exchange term around the hexagonal loop on the pyrochlore lattice. So effective Hamiltonian is basically a ring exchange model in this case. So physically what happens is that if you start with one of those 2 into our configuration on the lattice, and if I apply this ring exchange model, Then I flip the spin one by one. I flip this guy, this guy, this guy, this guy, this guy, this guy. Then I generate another configuration. And this configuration is also 2 into our configuration. And this configuration is different from this guy. But since it also satisfies the 2 in 2 out constraint, it's one of those exponentially large number of states. So if I keep applying this ring exchange operator on this configuration, I will generate another configuration that satisfies 2 in 2 out configuration. So by doing so, essentially I can generate all the possible spin configuration. So quantum dynamics connect all the degenerate manifold. So quantum ground state is really just a massive superposition of classically degenerate state. That's the way that quantum ground state can be a quantum spin liquid. So that's quantum spin ice. And there's a very interesting mapping to a quantum electrodynamics here. So you map the Z component of spin to an electric field. The creation operator, sorry, the spin creation operator to a e to the I vector potential. Then the commutation relation between G component of spin and the raging operator becomes a canonical commutation relation between vector potential and electric field. So if you think about electric fields as a coordinate, then vector potential becomes a canonical momentum. If you do that, then the 2 into out constraint becomes a Gauss law. The fact that cluster spin to be 0 becomes a divergence equals 0. And the ring exchange term can be mapped to a cosine curl of A. So lattice curl around the hexagonal loop. And remembering that my spin operator is a spin half object, SG square is always 1/4. So I put some constraint here by taking a large U. Electric field square has to be always 1/4. That's remembering that these are spin half operators. So the ring exchange model with this constraint maps to a lattice quantum electrodynamics model like this. And in particular, if you are in the so-called the deconfining phase of quantum electrodynamics, you can expand the cosine. And then you get a E square plus P square Hamiltonian like that. So you end up with some kind of mapping to a quantum electrodynamics. So using this mapping, you see that you can imagine having many interesting excitations. So first of all, there should be a emergent photon in the low energy that has a linear dispersion. The capacity should be proportional to Q. There's a spinon excitation. This is what we call an electric monopole. So that excitation should exist. And then there's also a magnetic monopole excitation. So it turns out magnetic monopole excitation is nothing but the fact that the curl of A equals to 0, curl of A equals 2 pi. They are degenerate. So there's a quantum tunneling process from curl of A to be 0 to curl of A to 2 pi, 4 pi, 6 pi. So those excitations are called magnetic monopole. Okay. Just to show you that this is not a complete fantasy, there was very recent experiments on one of those cerium-based pyrochlore material. This is paper that I collaborated with the Pengcheng Dai sitting here and the Bingao. And the heat capacity at extremely low temperature was measured for this material, and you get a T cube heat capacity. So this is the one of the strong evidence is that the quantum spinized material actually exists. And the estimated velocity of photon is 8 meters per second. It's a very slow photon. You can almost race with this guy. You can try to run. Okay. So it's a very slow photon. So, okay. So I think that's all I wanted to say. Thank you very much. Yeah. It's very hard to compete. Right?